Of course, in an earlier session, you've learned what an equation is and what an identity is, right? So I'm not reiterating those facts about what an equation is and what an identity. Both are mathematical statements. An equation is not true for all values of the variable. An identity is true for all values of the variables involved, right? That's the difference. Now, Px equal to Ax plus B. What's the highest power of x here? 1. This is a polynomial of degree 1 in x. This is a polynomial of degree 1 in x. In x. It's also called a linear polynomial. It's also called a linear polynomial. Say 3x plus 5. This is a polynomial of degree 1 in x, a linear polynomial, right? Is there a value of x for which this polynomial becomes 0? This polynomial will become 0 for x equal to minus 5 by 3, isn't it? For x equal to minus 5 by 3, this polynomial becomes 0. This is polynomial, just an expression. For different values of x, it will assume different values. That means the value of the polynomial at x equal to minus 5 by 3 is 0. The value of the polynomial at x equal to minus 5 by 3 is 0. That means the polynomial vanishes at x equal to minus 5 by 3. The polynomial vanishes at x equal to minus 5 by 3. Then the value of x for which the polynomial vanishes is called a root of the polynomial. Is called a root of the polynomial. So minus 5 by 3 is a root of the polynomial because at x equal to minus 5 by 3 the polynomial vanishes. How many roots does this polynomial of degree 1 in x have? One root. One root. It will vanish for exactly one value of x. A polynomial like this, ax squared plus bx plus c, is a polynomial of degree 2. It's a highest power of x is 2. It's a polynomial of degree 2 in x. And it's called a quadratic. It's called a quadratic. Now, say x squared minus 10x plus 7x plus 10 is a polynomial of degree 2. For different values of x, it will assume different values, right? Realize that this will become 0. X square minus 7x plus 10 will be 0 when x is either 5 or x is 2. It will become 0 at x equal to 2. It will become 0 at x equal to 5. It will become 0 at, that means 2 and 5 are the roots of the polynomial because p at x equal to 2 is 0, p at x equal to 5 is 0. P at x equal to 2 is 0, p at x equal to 5 is 0. Yes or no? Then 2 and 5 are said to be roots of this polynomial of degree 2 in x. 2 and 5 are the roots of this polynomial of degree 2 in x, right? A polynomial of degree 2 will have exactly 2 roots. A polynomial of degree 2 will have exactly 2 roots, right? They could be real roots or they could be complex roots. You realize that if I have a polynomial like x square plus x plus 1, if this was a polynomial, its discriminant is less than 0, 1 minus 4. Therefore, the 2 roots of this will be complex roots. If I have a polynomial px which is x squared minus 2x plus 1, this has real roots, but realize that this is x minus 1 whole square. It has 2 real roots. X minus 1 are the 2 factors. The 2 real roots are 1 and 1. They are said to be coincident real roots. They are said to be coincident real roots. Right? Discriminant is equal to 0 in this case. It has coincident real roots. Yes or no? Now, see, understand the difference between roots and solutions. this will become 0 at x equal to 1. That means this equation when equated to 0 will give me one solution x equal to 1 but two roots. These are two coincident roots. That means a polynomial of degree 2 can have two distinct roots, real roots, two complex roots, or two coincident real roots, or two coincident real roots. So a polynomial of degree 2 in general will have two roots, whether they are real or whether they are complex or whether they are coincident. Yes or no? And the same fact gets extended to a polynomial of degree 3. A polynomial of degree 3 is like this: ax cubed plus bx squared plus cx plus d is a polynomial of degree 3. It will have exactly three roots: real or complex, distinct or coincident. Real or complex, distinct or coincident, it will have three real roots. Important thing is, if it's a polynomial of degree 1, then a should not be 0, because if a turns out to be 0, it will be a constant and it will become a polynomial of degree 0. A constant is a polynomial of degree 0. So b can be 0, but a should not be 0 in a polynomial of degree 1. If it's a polynomial of degree 2, then a cannot be 0, because if a turns out to be 0, it will become a polynomial of degree 1. But b and c can be 0. If it's a polynomial of degree 3, then a cannot be 0, otherwise it becomes a polynomial of degree 2 in x. So, but b, c, d, etc. can be 0, not a problem at all. Yes or no? This is a polynomial of degree 3. It must have three roots. Exactly three roots. Whether those roots are real or complex, distinct or coincident, that's another story. Real or complex, distinct or coincident, but it will have three roots. It will have three roots. Yes or no? In a very generalized sense, a polynomial of degree 4 will have exactly four roots. That means four values of x, it will vanish. A polynomial of degree 5 will have exactly 5 roots. It will vanish for exactly 5. A polynomial of degree n will have exactly n roots, real or complex, distinct or coincident. That means if I have a polynomial of degree n, n is a natural number. Polynomial of degree n would be something like this: a naught x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus a3 x power n minus 3 plus up to an. This is a polynomial of degree n in x. This is a polynomial of degree n in x. The highest power of x here is n. The highest power of x here is n. This is a polynomial of degree n in x. These a0, a1 are coefficients of various powers of x. These are coefficients of various powers of x. And if it's a polynomial of degree n, all coefficients can be 0 except a0. a0 should not be 0, because if a0 turns out to be 0, it will become a polynomial of degree n minus 1. So other coefficients can be 0, but a0 should not be 0. That means coefficient of x power n should not be 0 in a polynomial of degree n in x. Yes or no? And the rule for a polynomial of degree n in x's must have exactly n roots, real or complex, distinct or coincident. Call those alpha 1, alpha 2, alpha 3, alpha n. Not all have to be real. Not all have to be distinct. There can be some roots that are real, some roots that are complex. But they are n roots, exactly n roots in all. If alpha 1 is a root, that means the polynomial, when you replace x by alpha 1, it must become 0. That means a naught alpha 1 to power n plus a1 alpha 1 to power n minus 1 plus a2 alpha 1 to power n minus 2 plus an must be 0. At x equal to alpha 1, this expression must vanish. Similarly, at x equal to alpha 2, put x equal to alpha 2 in this expression must vanish. Put x equal to alpha n, this expression must vanish at x equal to alpha n. Yes or no? Clear? So do you understand that a polynomial of degree n, where a naught is not 0, obviously otherwise it will not be a polynomial of degree n, must have exactly n roots, real or complex, distinct or coincident. Stand by. Now. Agla clip,